Thank you very much for inviting me. It's an honor and kind of an amazing experience to be here. No, microphone not? It is on. Maybe I'll move it. Lower? Okay. How's this? Okay, great. Thank you. Right. So actually, after the last talk, I feel that now I see the purpose of my talk, which is to bring the kind of accessibility level back to average. So it's going to be very elementary. And it feels like kind of, it's a birthday conference. I wish I could bring some big complicated birthday present, but nothing is finished. And so it's like one little thing that, it's like somebody from kindergarten makes a nice card and brings it and kind of hope to bring this nice piece of work to you. It's actually joined, but mostly done by them. It's like self-contained little thing that doesn't seem to be directly related to Arthur packets or anything that people are talking about here, but hopefully it has some useful pieces. It's done mostly by two wonderful young mathematicians, Itai Glazer and Yotam Hendel, and so there's been a bit of a fashion of putting people's pictures into the talk, and I don't really have their pictures. We didn't know each other when we started this project, so this is a picture to remind you of the great Zooming times of COVID. This whole project started when well, there was a conference that was supposed to be in person, and of course I don't remember where it was supposed to be because it wound up being on Zoom. And I gave a talk about my usual motivic integration something, and that's where I met Yotam. Oh, no, that's not supposed to happen. That's where I met Yotam and Itai, and they asked me some questions, which you will soon see, and so we started talking, and so then the whole project was done on Zoom. Basically, from my end, it was just talking on Zoom once in a while, and they did all the work and took it to some interesting directions, and kind of I'm honored to be part of it and talk about it. So anyway, so what it's about, it's a few kind of slightly disjointed things. So the main culprit is Fourier transforms of nilpotent orbital integrals and kind of how they're controlled in size by various ratios of Wild discriminants, which thanks to all the symmetries that exist in the Lie picture have some really nice, there's some nice formulas that come out that I want to showcase. And there is something that I learned from this collaboration, which I feel like it's very useful for all kinds of things I do, but it hasn't yet translated to any results on my end. So, but I want to share this, and probably I'm aware that there are some experts in this room who probably knew this for a long time, but I just learned this. I'm happy about it. And then there are applications which I think are very far from anything that anybody here does, that Yotam and Itai took that in that direction, and I think it's just cool stuff, and I will try to do it justice if I can. All right, so the definitions as usual, the usual notation. Okay, so now I want to focus for a moment on defining the Wild discriminant. I know you all know it, but we will need its special features. Yes? Of course. Sorry, I was too scared. At some point, there will also be a definition of an orbital integral, which also will be flashed very quickly. So no, just notation, and I will go over it again. It's not important. Yeah, so the next one is more important. I'm going to go to it. So yeah, G is a reductive group. So actually, maybe I should have mentioned on the previous slide. Fine. That I will be very ambiguous about whether G is a p-adic group or a real group or a complex group. The definitions, I think, because I always work with p-adics, all the definitions and all my normal setup is going to be p-adic, but then in the end, I want to show some results for real and complex groups, which are exactly like that. So, but when I write something like the local character expansion, it will be an equality like it is for the p-adic case, right? Not an asymptotic equality. So you kind of have to stretch it a bit to realize that, yeah, like pretty much everything I say with some obvious modifications holds for all kinds of groups over local fields. However, not in positive characteristics. So now the next fun thing is that, I spent 20 years, I think, since last time I was here talking about how to transfer everything to positive characteristic. And this thing, we thought it was going to be automatic. And in the end, we had to cut out the last section, which was called transfer to positive characteristics, because there are technical difficulties that we did not anticipate, even like with all the work that's been done on this kinds of transfer for analytic questions that I thought I knew all the answers. And then there are all these little catches there. So one day maybe we'll do it if we're motivated, but I don't know. So, okay, fine. So anyway, so I'm going to just define the wild discriminants. And as you know, so if you have an element, a semi-simple element in the Lie algebra, it acts by the joint action, right? So one can look at the determinant. And there are several cool formulas for it, right? And so one of them is that you can write it as a product of the absolute values of the roots. And then, well, what gets this project started is the fact that, so so this is on, well, when I say, what I want to say, I guess, is that if you look at the same Cartan subalgebra that your element started in, then this is just a product of linear terms. So from the perspective of algebraic geometry, it's a very simple polynomial. And it's an absolute value of a polynomial. Sorry, I should have said. Yeah, they are. And so, yeah, so, but so it's, I should have said it's an absolute value of a, you can kind of think about it as an absolute value of a polynomial. And the zero set of that polynomial, well, the set of non-regular elements on T, it's a hyperplane arrangement invariant under the wild. And so that's what kind of gets the whole thing started. Okay, so then of course, you know, so we're going to be talking about orbital integrals and characters. I don't want to keep this slide on for very long, but I can. It survives. I think pretty much every talk of mine has the slide, so it gets copied from my talk to the next. Let's see. All right, and so then this also gets copied from my one talk to the next, typically. So the point, that was the starting point of this project for us, is that the distribution character, you know, thanks to Harish-Chandra, by very different proofs in the real and p-adic cases, is represented by a function that's locally constant on the regular set, but gets big as you know, the neighborhoods in which it's constant get smaller, and the function gets big as you approach the singular set. And a difficult theorem that it's locally integrable, meaning integrable on compact sets. And the same, sorry. The same is true for Fourier transforms of all orbital integrals. And moreover, what's important is that this wild discriminant from the previous slide to the power 1/2, but the thing is, it looks like a square, right? Because you're taking a product over the whole root system. So the square root of it bounds on compact sets, provides a bound for the blowing up of the characters in Fourier transforms of orbital integrals. And so, yeah, and we also have the local character expansion. And so the wavefront set is the set of nilpotent orbits for a representation that appear in the expansion of its local character. And that's exactly the thing that appeared in Professor Zhang's talk yesterday. And so the question that started it was, it actually came from this whole motivic integration business, where Yotam and I have done some work. So I had proved years ago that with Raf Pluckers and Mikhailov joke that all these functions that you see, this the characters and or Fourier transforms of orbital integrals live in the so-called in the class of so-called motivic functions, whatever they are. Yotam and Itai recently, by a rather ingenious argument, proved that if it so happens, and it was for a different reason, actually, they were motivated by some questions in algebraic geometry, but they proved that if a motivic function lives in L1, then it has to live in L1 plus epsilon for all epsilon. Sorry, for some epsilon, I meant to say, that it cannot be, I guess, the set of, what it's saying is that there is no, that the infimum is not reached, right? That if you're in L1, then you have or in L2, then you have to be a little bit bigger than that it's open on the left. Okay, and so they asked me whether it's somehow known what is the epsilon, you know, if you're given a representation somehow, what can you say about the improvement on the local integrability for that representation that you can make? And I realized that I had never seen this question before. Yes.
Motivic, I mean, we understand that in the book theory case, you expect these properties, but
for real, right? Yeah, I don't know. So the thing is that it's the only time I have to use it. It's just an explanation for why they asked me this question. So it's completely not relevant for what will happen in the talk. So it's just somehow you can say that there is a good reason to believe that, well, even though, there's a difficult proof that this characters, orbital and Fourier transforms of orbital integrals are locally integrable, there's good reasons to believe that this integrability exponent can be improved a little bit. But that's all. Yeah, that's right. It contains all these things that Igusa considered. And so it's basically a very specific class of functions defined by means of model theory. It's got a bit expanded, but it's this stuff. So anyway, we've been doing it. It had its purposes, but for the purposes of this talk, it's completely irrelevant. But those functions are kind of known because they come from a rather constrained class of functions. It's known that they cannot have too complicated analytic properties. And so in particular, if they're an L1, they have to be an L1 plus epsilon. So we're going to try to improve the epsilon. And of course, trying to go through the work of Harish-Chandra is not very likely to improve any constants or epsilon. You kind of see that it's very difficult and quite indirect. And so, but then of course, you look at it and you say, well, as a first approximation, of course, everything is going to be controlled for a representation. It should be controlled by a local character expansion. Oh, sorry. And so, yeah, and so anyway, so these are the two questions that we started with, which is, given a representation, how much can you improve it for a given representation? And that very quickly, oh no, why does this happen to me? This very quickly tells you that you should be looking just at the wavefront set. And so the natural question then is, how much can you improve it for the Fourier transforms of orbital integrals, of nilpotent orbital integrals, because there's this finite improvement. And that the first one, if you just want a general kind of some epsilon that works for all nilpotent orbits for all groups and therefore for all representations, it's easy to answer, as it turns out, thanks to a coincidence kind of also from algebraic geometry. So there is a notion of a low canonical threshold that has its own history. A very natural thing, which basically is given a, say, analytic function, a log canonical threshold of that function, is it's kind of an invariant of singularities of its zero set. It measures, how far can you push the S so that the function remains integrable on the ball around a given point. And so this luckily has been studied by algebraic geometers. I'm running ahead of myself. And in particular, so yeah, it's an invariant of a singularity, but different from other invariants of singularities somehow. But if you can have a nice sequence of blowups, then again, Mustata, I think, gave formulas expressing this low canonical threshold in terms of the data associated to blowups. Looks very Gusa style. So it's like, it's not a coincidence that the same kind of gang of people was working on it. And so, yeah, and so especially, but then it turns out that especially in the case of a hyperplane arrangement, the blowups can be kind of parameterized. You can understand everything just from kind of what's called an intersection poset that's associated with that hyperplane arrangement. You kind of basically count the intersections of different hyperplanes. It's a completely combinatorial thing. And so we were very lucky. So when we realized that that's all we need, we looked at it and realized that also in our special case, because this hyperplane arrangement is so symmetric with respect to the Weil group, the answer comes out very nicely. And so the answer that works for everything using this method of the hyperplane arrangement came out to be just 2 over the Coxeter number. And that's because you just take the Weil discriminant itself and this works. And then, yeah, that's for a simple group. And if you have a reductive or semi-simple group, then you have to take the minimum of these over the simple ideals. So yeah, I think I already mentioned. So the method of proof for that was, well, there is a bit of a complication here that happens. So on T, it's a hyperplane arrangement, right? Like if you fix a Cartan, suppose you're working over an algebraic closure for simplicity for now. You fix a Cartan on it, it's a hyperplane arrangement, then you have your low canonical threshold. How to get back to integration over G? Well, of course, there is Weil integration formula that also gives you some power of the discriminant. So everything somehow nicely balances out. I mean, yeah. Sorry, can you say it again? Yeah. So yeah, so no, so this is for now. See, right now I'm not talking about. So the question was, how does this low canonical threshold of the discriminant relate to orbital integrals? So far, I haven't said anything about orbital integrals, right? It's what's happening is, sorry, just a second. Here we are. Because both the characters and orbital integrals, once you multiply them by the discriminant to the 1/2, become bounded. You realize that it's exactly the low canonical threshold of the discriminant that controls them a priori, just from Harish-Chandra. So that's exactly the point. And so then we focused on the low canonical thresholds of the discriminant, and then we were able to compute it on the nose that kind of just came out very nicely from existing stuff. Then, as they were writing it up, Itai and Yotam also found that, in fact, Obdam, many, many years ago, has actually computed this quite explicitly by a completely different argument. What happened? Yes?
We really not the addict because a few slides ago, the article was locally constant.
Yeah.
And now it never goes in. So
no, so that's what I'm saying. So, right, so our proof, so thank you for that. I mean, I'm being a bit sloppy. So what I'm trying to say is that our proof here is p-adic. You know, we really were focusing on p-adic things and like later maybe, but our proof also works for complex because for now it's mostly over the algebraic closure. So our proof mostly works for complex because it's, you know, the low canonical threshold is the same way.
Obdam does it for real.
Yeah, Obdam does it for real and complex, but this is a completely different situation. So his paper is focused on. He was actually trying to prove a conjecture. I mean, he was proving a conjecture of MacDonald. He introduces this hypergeometric shift operators. And they basically are a very clever family of things that allow you to integrate by parts in some sense. It's like it's a really souped up integration by parts. I think it's for complex group also. So I don't actually, we haven't checked, but it looks like an, I mean, but it has to, I think for kind of abstract reasons, this low canonical threshold has to be the same for the complex and for the p-adic cases. Which one? Oh no, the low canonical threshold. Oops, yeah, I mean you can have a p-adic ball. Sorry, it's that's general. Yeah, taking a p-adic ball is completely fine. So the absolute value of f could be Archimedean or non-Archimedean. So that's a very kind of general. So yeah, then one has to be a bit careful. So that's why when I say p-adic, at the moment I mean really p-adic and not local field of positive characteristic, because so far our methods rely on resolution of singularities, which in positive characteristic doesn't quite. So can't quite. So this algebraic geometry thing does not work. And as you pointed out correctly, the Obdam's approach is really very much not p-adic. You certainly cannot do integration by parts in the p-adics, and that's what leads to this whole thing with monodromy conjecture and so on, if you only could. So anyway, so but we didn't know about it, but I was very fascinated with this Obdam result, and so we kind of added it as a, and it gives the same answer, reassuringly, as you would expect. But completely different method. But the thing is that he multiplies it by the Gaussian and then literally computes it on the nose over the ball. And because the Gaussian is approximately 1, it gives you the information about low canonical threshold. So, okay. And so now the point is that, so that was a very quick kind of and a pleasant answer to what can you do the most generally. So it means for all representations and for all Fourier transforms of nilpotent orbital integrals, you can improve their integrability literally in the Harish-Chandra's theorem by 2 over the Coxeter number. Okay, and but then somehow Itai was not satisfied with that. He said, but wait, you know, I know for a fact that for some things epsilon can be improved a lot. For example, you know, take the trivial, you know, take the 0 orbit, then you know, epsilon is infinity. So once you have experience with these things, and said for some representations that he cared about, he felt like it could be a lot more than 2 over something large. And so then so the rest of the talk is about what can you do for individual orbits. So then again, oh yeah, so coming back to this, so then he actually wanted to know what can you do for individual representations, but then thanks to the local character expansion, I'm still thinking p-adic, it immediately reduces to kind of, well, not completely, but you look at the local character expansion, and in some sense, like you would think that the worst singularity of like whatever the worst orbit in the wavefront set is would be it, or at least it would give you an epsilon that works. And so, so then it immediately reduces you to a question of what can we do for Fourier transforms of nilpotent orbits. And for that, in general, we unfortunately only have partial answers that are kind of instructive, but for GLN, it's everything. So the second part of the talk would be results for GLN. And for general groups, it only works for the orbits that are Richardson. And so, well, an orbit is called Richardson if there exists a parabolic such that our orbit is dense, Zariski dense in the unipotent radical of that parabolic. So notice that it's kind of very different from, the Valacarta parabolic. I'll talk more about this with specific examples in GLN. And so in this case, if you have such a parabolic, then the decomposition of its Lie algebra is called the polarization for O. Okay. And so, okay, now, so there is this, and this is a completely separate kind of part of the talk. So there's this geometric construction of Fourier transforms of nilpotent orbits that I learned from Yotam, who probably learned, I mean, I think he came up with it, but I think it's based on a lot of conversations with Bernstein. And it's something I did not at all know, and I got very happy about it somehow. So I want to present it at some level, but it's probably known to some people here. So one starts with the flag variety associated to the parabolic. So we're starting, so at the moment our group is arbitrary, maybe let's say p-adic just because that's my comfort zone. You consider the flag variety associated to its Richardson parabolic. And then, well, this is the generalized Springer resolution that lives there. Yes, I should have said that. It can be identified, so this variety can be interpreted as the cotangent bundle of the flag variety, and that's what really enables the calculation. So there is the G action, and so the key point here is that when O is Richardson, and so this Zariski density statement holds, that means that the dimension of this O twiddle is the same as the dimension of O. So you actually get an Étale map. And then when you push forward some differential forms, and that's what's going to happen in a moment, then you acquire some maybe finite counting coefficient, but you can explicitly write down some very natural differential forms and do everything just in terms of push forwards and pullbacks of these forms. And yeah, and that, so if O is not Richardson, then this really doesn't work, and I really wish I knew what works. But that's kind of for future work, maybe. Yes. It's the blue part that fails when O is not Richardson. So it. Oh, sorry. Oh, okay. No, so it's the Étale part that fails. It's O is bigger dimension when O is not. O twiddle is bigger dimension than O when O is not Richardson. And so there is this extra dimension, and it also shows up. There's this paper by SM where he proves that orbital integrals converge. It's like 6 pages, which I felt like I never really understood. I've been returning to that paper since my first year of grad school. And okay, I mean, line by line, you understand it, but like it's really, I still don't understand what's going on in some sense. And there is this character that you need to introduce on this piece called G minus 1, in which your element acts by -1. That also appeared in Professor Zhang's talk yesterday. And it's exactly that. Like when O is Richardson, that whole thing is also not there. So it's kind of, you can see it both from Valacarta side and from the Richardson side, that somehow these orbits are much nicer, and I don't know why. Anyway, but so when that piece is not, so when it's basically it's this G-1 troublesome piece that like if it's there, then I don't know what to do. But as it is, we can write some very natural differential forms, basically. So, and this is another kind of ingenious piece. So there is this constant Kirillov constant form, they both start with a K, so I don't know, that lives on coadjoint orbits. You could identify them with orbits, and so you get that two form. And there's also a very natural two form that just lives on the cotangent bundle just because the cotangent bundle. And so you can get a volume form by taking D products, by taking a wedge product of itself D times. And so these are the very natural forms that live on everything. On the unipotent radical and on the opposite unipotent radical and so on. Okay, and so now when you're doing the Fourier transform, so well, I should have actually I should have maybe written down something here. How am I doing on time? Oh, I'm not doing too badly, so I can actually write this down. Sorry. I should have maybe made one more slide. I didn't think of that. Is the board still going to be visible? So the Fourier transform on G on the Lie algebra is defined by, for functions, right? It's the integral over G of f of x. This is some additive character of the field. Fix it, it doesn't really matter. It will just introduce some constant if necessary. So this is some G invariant, non-degenerate bilinear pairing. So pretend for a moment that G is semi-simple, and so we can take the killing form. In any case, we kind of do everything for G simple and then make various direct sum arguments to generalize to reduct. So, so the key point that enables this is that with respect to the killing form, so if you have a parabolic, so some Cartan plus maybe some, I don't know, L plus N, alpha Levy. Then with respect to the killing form, the orthogonal complement of N is P. So where the perp stands for orthogonal complement with respect to and so, sorry, should have written notes on paper or something, but okay, right. And so what we're doing here is, so yeah, so just trying to explain the first line on the slide. And then, so now, if we want to do, right, so first of all, Fourier transform of distributions as usual. Is the distribution applied to the Fourier transform of the test function. And now, so we're doing things on the flag variety cross G. So we just kind of think about it as kind of a bundle living over the flag variety and do a Fourier transform fiber-wise. So on the G coordinates. Okay, so with this in mind, so we have this O-twiddle, so we can define this O-twiddle perp that lives there, right? And then just carefully track all these various projections that we have and carefully track the differential forms. And so the key point is that, how to say this, because the killing form pairing kills the P. So the Fourier transform very loosely speaking, so one can, I mean, it takes a couple of pages of lemmas to track through all these forms and what they're invariant with respect to and so on. But more or less what we're trying to say is that Fourier transform amounts to just integration on n minus. So that's more or less all that happens, because that's all that's left of the G once you've taken care of the vanishing of the killing. And so the upshot of that is that the Fourier transform of the stable, so yeah, at the moment actually, so I realize that I've been ignoring rationality questions completely. So this is a geometric argument, and so we're thinking about everything as a variety over an algebraic closure. So over the algebraic closure, the Fourier transform of the orbital integral, and that's why I put stable here. So the Fourier transform of the stable orbital integral can be thought of as just the push forward of the form that lives on O perp, and the form, this natural form that lives on O perp is basically just the natural Haar measure on the n minus coordinates. So, and that's a bit shocking because of what's on the next slide. So, as a distribution, yeah, just an integral over the whole stable, integrating your test function over a whole stable orbit. Because for the moment, this is all over just, this is happening over the algebraic closure. Okay. Sure. Yeah. No, so on the left, so this is all thought of as kind of, everything is thought of as measures or distributions on the space of test functions. So this is kind of a equality of distributions. It's not a density function yet, but we will see for the density function, it's coming on the next slide. Well, it takes, so yeah, maybe let's decipher it. Yes, Dasha is asking what's the right-hand side as a distribution. Maybe I should write this explicitly, sorry. So just a second, don't make mistakes. So let's put it this way. So we have this, let's write the distribution C O twiddle perp. So what it does, it basically takes your test function and integrates it over O twiddle perp with respect to the natural measures that lives there. It comes from this differential form that we just discussed. Okay, and so then so by definition, what I want to say is this: it's I star perp. So I'm trying to keep notation light. So let's, in a moment, I'll explain what I'm trying to say by all this notation. So I kept it off the slides. So this is just a measure defined by the differential form omega twiddle perp, which is simply omega n minus wedge omega p. So basically you start with something that's just a Haar measure, you know, invariant on one side and transforming by the modulus character on the other side. Take the measure related to that form. Then, so this I perp is the embedding of O perp into P cross G. And then you push it to the whole space. So that gives you a distribution that's basically, you know, it's concentrated on O twiddle perp and just integrates with respect to the natural measure. Okay. And so kind of the key identity that maybe in retrospect I should have put on the slide, but now I can put on the board, is that so if you just do it with respect to n minus coordinates, so I'll write it down and try to explain like what all the notation means. So I didn't put it on the slide because I didn't want to deal with notation. You know, it's a technical question. But I think since I have the time, I can do it. So the key to this whole thing is this. Okay, all right. So what's written here? So the J is the corresponding embedding of what? Yeah, there is basically the embedding of n, and there is an embedding of p into these bundles. And so you start with this measure on n minus cross n, and then you push it to a measure on n minus cross g, basically. And if you Fourier transform it, then and that's a calculation. So this is not something that should be obvious to you right away, but it's like a one-page calculation. And the calculation is based on very carefully tracking what these forms are invariant under. So it's actually also a little bit like Rangarao, where he doesn't, he proves that it's a hard measure just because it's invariant. He writes the measure in a particular way and proves it's invariant. And so it's kind of the same idea that you look at these forms and check their invariance at the same time. And so, but the point is that, and so this is kind of an amazing thing, because it's just a carefully tracked. So, so all I'm saying is that high up on the Springer resolution, you can just take Haar measure on like a piece of your group, right? On the unipotent radical, wedge it with something of the correct dimension coming from somewhere else, which is just Haar measure. And then the Fourier transform gets hidden in this push forwards and pullbacks that we're doing.
When you have values in these the forms are always in top degree,
Yeah,
right?
yeah, all of these forms are in top degree. That's exactly right. Yeah, and so that was kind of a piece of magic that I've learned from your time. And so it leads, it's because I'm holding it upside down. That's why it goes back. That would do it. So it's like, why is it wrong arrow? Okay, so yeah, not invariant under that kind of flip. So all right, so this leads to a pretty amazing formula for the density of this distribution. So this FO is, this Fourier transform of a stable orbital integral is going to be represented by a locally integrable function, right? And I honestly used to think that I will never in my life know exactly what that function could look like, right? But it's just like those kinds of things. I mean, orbital integrals are bad enough. Fourier transforms of them, I don't know. And then it turns out that it's just like a sum of ratios of discriminants with respect to, as you go over the conjugacy class, because, because you're computing this guy, and this is basically a form, that there's this finite cover that's playing a role in that, and on each one of them there's the Jacobian, right? It's just like you write the usual Jacobian formula for measures. You start with this extremely natural form upstairs, you multiply it by the Jacobian. The Jacobian is, of course, exactly the Weil discriminant. That's kind of exactly the same calculation that goes into Weil integration formula. And so it turns out to be this. And that really surprised me because, but I mean, in retrospect, shouldn't have been all that surprising, but it's a Fourier transform of something. So I would expect some kind of exponential sum or something in there, but it's rational. But then on the other hand, it was kind of funny because, well, Lauren and I have been working on a paper that, I've been promising for 10 years, it's only 10. So where we're trying to prove that characters are motivic in that certain sense, whatever. And there, I keep finding a very strange thing that, once in a while, Fourier transforms, you expect orbital integrals to be rational. And then you expect that when you're doing a Fourier transform, then some kind of exponential sums related to the character come up. But on the other hand, I mean, as many, many experts here know, is when you're working with these orbital integrals, they very often give you, how to say, the Fourier transform of an orbital integral gives you a character. When you integrate that character against something, you get the multiplicity of that something. So you should expect a lot of rational values out of these Fourier transforms. And some Gelfand-Graev stuff is responsible for it. I'm still a bit puzzled by that. But I think this is another kind of very clean situation where, so apparently for Richardson orbits, they're just rational, at least the stable ones. So maybe there is some very complicated exponential sum that goes into each individual, component of the stable orbital integral, giving you some signs. I don't know, but at least the stable orbital integrals are very easy. It is surprising. For Richardson orbits, right? For Richardson orbits. So yeah, what we've learned from this is that for Richardson orbits, stable orbital integrals look super easy. Sorry, Fourier transforms of stable orbital integrals look just like this.
But also these are stable conjugacy classes.
Yeah. So this is a stable nilpotent orbital integrals. No, so these are actual conjugate. Like the y's are these. Oh yeah, stable conjugacy. I should have said stable. Yeah. Okay, great. And so now let's go to GLN, where all orbits are Richardson, and then we can get everything. So, and also all orbits are stable, so it's really nice. So that disappears. Okay, and so now a small piece of combinatorics, the notion of a conjugate partition. So partitions correspond to Young diagrams, so you just transpose the diagram. So here's an example. So there is a correspondence between nilpotent orbits and partitions. And on the other hand, partitions correspond to parabolics. And so under this, the Richardson parabolic is given by this conjugate partition. And that's in Collingwood-McGovern. I don't know how that magic works. I mean, I read it every time, but it's still counterintuitive to me. I don't have any, I would say I don't have any insight on how that magic works. All right. And so then using all this, now coming back to our original question. Oh yeah, sorry, just a sec. So because we have this formula for, well, stable orbital integrals, but they're now orbital integrals because we're in GLN. These are discriminants. We know exactly how they're, we can track the hyperplane arrangements attached to them. We know how to blow up those singularities. We feed the whole thing into the Weil integration formula again, and we obtain this theorem. By the way, when I say we, I really should say they, like they've done all the work on this. So, so it's kind of slightly nasty in a combinatorial way. Well, because, and you will see in a moment, it's a genuine difficulty. So for a while, we tried to figure out, if there is some nice thing. We even asked some colleagues who do combinatorics if they've seen these kinds of things, but we didn't get any like obvious simplification of that. And in a moment, you will see why. In GLN, however, a very nice thing happens also is that this epsilon, it's possible to prove that this epsilon respects the orbit closure relations. Generally, we don't know. All right. And so now, so that came out from the blowing up of the singularities. Alternatively, from this geometric description, one can obtain a formula that's kind of very geometric. It's also a minimum. It's basically the same formula, but kind of dressed more nicely. Okay, so an example of all of this is that if you take a maximal parabolic, so kind of easier to start with the parabolic than with the orbit. So suppose the maximal parabolic, was a J block and an n minus J block turned out to correspond to some nilpotent orbit. Well, the orbit would be this. So then it turns out that minimum, like you evaluate all of that, and the epsilon is 1. So it means that it's just, so it just fails to be an L2 because it's 1 plus 1. Okay, and so this is, yeah, now the question is how to make it bigger. Just a second, I'm going to, oh yeah, sure.
So for all J, this is just barely not an L.
Yeah, yeah, yeah.
I would have expected just for J equal to, well,
I think it's for all J. I'll double check. Maybe I miscopied, to be honest. I don't feel complete ownership over these things. I am hoping that I'm not introducing errors into what they wrote. I think that's what it is.
Reasons to expect L2 when the two columns were the same size.
Ah, okay, but maybe it's for, so yeah, all right. So it's actually good to talk because so okay, at least I'm glad that it's not too far from what you would expect. So that's certainly good news. Okay, and so yeah, I don't know how to make this bigger. Just a second. So I'm going to try something. Wait, is it the Windows machine? Does anybody know how to make the screen bigger on the Windows thing? It's not mine. Oh, okay. Control plus works. Okay, great. So this is an example of, so they got a computer and they got it to compute the minimum. Just to see, we're just trying to see if this minimum behaves nicely so that we would get a conjecture for how to simplify our formula. Yeah. I hope so. Okay, and then I'll move it. So, so this is a graph of orbits with respect to closure relations. So rather partitions corresponding to orbits with respect to closure relations. In blue, you see the epsilon. So can you see the epsilon? Yeah, and so so you see there are kind of it doesn't always. So okay, it's yeah, there are some strange numbers like 1341st. Then for a while it's so it's really kind of it's all over the place. And then eventually, so it still does get bigger as you go through. Oops, no, that's not what was supposed to happen. Sorry. Okay, yeah, and so so this is a zero orbit at the end, and epsilon is infinity as it should be. Sorry? Yeah, so these ones are, so epsilon is 1, which means they're just barely missing L2. So it's like it means you can add anything but exactly the value of the epsilon that that we've computed. Epsilon star is a supremum of those things, doesn't have to be reached. So okay. And
what should be epsilon to be L2?
If you really want it to be in L2, then as long as epsilon is just a little bit bigger than 2, then you're fine. Bigger than 1, I meant to say. If it's just a tiny bit bigger than 1, if it's 1.1, because if it's then if epsilon was just like a little bit bigger than 1, then anything up to that would work. Yeah. Yeah, so that's the case for GLN, but for other groups, I think we even have a counterexample or something. It doesn't have to. If that formula as you evaluate it doesn't have to be. So, oh, actually, no, I'm not sure about counterexample. I think at some point we thought we did. So yeah, the answer is we don't know for other groups. We only know for GLN it decreases, and that's part of the theorem. But for other groups we don't know. Honestly, I don't want to say. Oh, okay. So now let's see. I have how am I doing on time? Oh, so which is how much I have? Oh, I have a full hour, not 50 minutes. Okay, maybe. Okay, so now, so this is a funny situation because it would be really good to be timed out of this because I don't know this stuff well. But on the other hand, I want to do justice to their results. So multiplicities of k-types. So and then when I say k-types, it's kind of like in some sense it's not. It's not Bushnell-Kuska k-types. It's so they call k-types anything. Basically you have a representation, some maybe even of a real group, whatever. You restrict it to a compact subgroup and look at the reducible representation of that compact subgroup. That's your k-type. So there was no other decorations that we're used to in the empirical. And so so for completely other reasons that that are of interest, like I think in other fields of math, like word maps, which you will see very soon, they're interested in the dimensions of, the multiplicity of, so suppose you have a compact subgroup, you restrict your representation to it. And so then the question is, how can do you have any relationship between the multiplicity of the representation and its dimension? So of course, there is a, formula for the whole decomposition of the right regular representation, but the question is, can you get any improvements? And so what comes out by kind of usual harmonic analysis tools, so once you have an improvement on the integrability of a character, right, then you can feed it into the into this direct sum decomposition. You restrict to a compact subgroup, you know that the character is integrable. And so then kind of by the standard methods for estimating kind of Fourier coefficients, which these multiplicities are in some sense. Well, I'm not saying it should be immediately obvious, but one does get the estimates like this. And so here the epsilon goes all the way up to our integrability threshold that we have just computed, that we have seen on the previous slide. So what we see from this is that somehow the more tame the wavefront set, so the bigger the epsilons we can get for the orbits participating in the wavefront set of our representation, the better bound we get on the dimensions. And there seems to be, so there's apparently a lot of literature on these kinds of things, which is, it's related to things like convergence of the zeta functions associated to this representation counts in finite groups and so on. So there are reasons to believe that this is probably fairly close to tight, but I don't know those, and so I don't want to talk about it. Okay, and next, so now switch to Lie groups, to real Lie groups, and so sorry, yeah, this looks like it. Well, but you know, the thing is that once you are, yeah, I guess here, you're saying that epsilon shouldn't go past 1. Yeah, in this formula, maybe we should have said something like that. It should be for finite epsilon, or you get nonsense probably. Yeah, so when epsilon is 1, you wind up with just saying that these multiplicities are bounded, which is actually perfectly reasonable because basically, well, at least if you knew that all of this is in L2, then those multiplicities would have to be bounded. So if the character were in L2, so this is actually consistent. Okay, and so now, basically the same formula holds for this is the very similar minimum thing over the levies that we had seen before. It holds for real groups. And so you get information for kind of this full L2 of K mod L, or the full kind of regular representation. And from it, so the cool thing that maybe, so, oh, I know what happened. It's because it's still in the plus. Okay, yeah. So so there is this last little thing that I want to say just for a minute, maybe. So you get an, it's okay. I don't want. It's a technical question. I don't want to talk about a real group. I don't know anything about them. Yeah, so but so the point of the previous slide was, not seriously, it was to get you to this slide. It's because what we want to do is we want to say something about the moments of the distribution of random matrices. Imagine, of all things, you know, I never talk about such things. So so this is entirely like your time and the Thai world, but it's really cool because yeah, so if you have a word like x goes to its Lth power, where L is just some fixed number, then you can push forward the usual measure on the unitary group, and that tells you about the distribution of powers of of random matrices. And so you can write a moment. And well, now we have estimate for this moment. So it turns out that this previous thing that on the slide that I didn't want to show Yanis in great detail, the reason for that was that there is some big minimum. But it turns out that when you're dealing with a unitary group, there are not that many levies, and somehow very magically you can evaluate that minimum. And it turns out to be something very simple. So that horrible minimum that you didn't have to look at for long just amounts to this in that case. And so you get a bound for the moments of the word maps. L is the length of the word. It's like you're trying to look at the distribution of the power. So your word is just x goes to x to the L. Only see color chart. So so you're looking at x goes to x to the L. So that's the L, and n is the unitary group. So it's an n by n unitary matrix. Tau is the push forward of the Haar measure on the unitary matrix with respect to this word. So it's the distribution of the Lth power of x, and you're computing its moment. The A's are the moments, and so you get an estimate on these moments of word maps, and that's, you know, all I can say is that some people in some field really care about this, and I mean it sounds cool, but I actually don't know that enough about that to tell you why. Sorry about that. But I think maybe somebody here knows more about it than I do, and so then you might appreciate that this is something worthwhile. Anyway, thank you. I think that's it for now. Oh, wait. This is important. Next slide. So, right. So, so yeah, thank you. I wanted to say happy birthday to Jim and thank him very much for supporting me here as a postdoc 20 years ago. Thank you. Well, I was mentored by him and Henry Kim and Fiona, and I'm really grateful for that. And I don't have any embarrassing photos of Jim from that time, but I found a photo from that time of very frozen Niagara Falls. And so this was just, you know, I just thought that this was really funny with, so if you didn't like the talk, this might be the suggested facial expressions, like, all this, all the haze from the falls froze on things. And then, but then, as I was preparing this talk and I put this photo in, I decided the last thing I want to do is like, well, I wonder, who was the person on the plaque who got to look like this? Well, maybe a quiz. Does anybody know? So this is the metal plaque at Niagara Falls. No, you can't see it because he's been totally kind of defaced by the ice. So you will. The photo contains no hint. I can expand it all you want. It's a plaque to somebody in Niagara Falls. It just got frozen over, and so it looks like a very grumpy gnome. But no, completely unrelated to math. So what I found from Wikipedia. Huh?
You don't know that.
No, I don't know anything.
One of the professors I had as an undergrad.
No, I know because I Googled, So so I Googled this, and Wikipedia pretty quickly told me, okay, let's guess the profession of this person, since I have 1 more minute. Right, engineer, that's what I thought. Maybe somebody who put up that power plant or something like that. Right? This natural gas, no. Military general, politician, all of that. No, so the answer is a poet. So from 1825, who wrote an ode, Jose Maria Heredia, who was born in Cuba and who wrote an ode to Niagara Falls because he was exiled from his beloved Cuba. I read the poem, and actually it was just so surprisingly relevant, even though, okay, it is romanticism, so there's a lot of pathos in it, but as you read it, it's like it could have been written yesterday, well, minus the pathos and romanticism. And so, yeah, you can Google this and find out, and there's like one last little gift of the poem maybe that somehow came out of this talk. Thank you. Thank you very much.